Okay, so we are back again for the third lecture, and a few things, but before we go over to other things. Now, let's do very quickly, reminding you that this is the radius of the cation if the coordinating an ion is 1.40 angstroms. So if you do that, then Rc for a coordination number of 2 is 0, the value should be less than 0.217 angstroms. Then see, none of these major elements which make up the bulk, 99 to 100% of your rock, they fall in this. So there are no elements that will have a two-fold coordination. And then we go to the next number, radius ratio 0.155 to 0.225, and you have a coordination number 3 oxygen atom arranged in a plane or whatever it is, but 3 nearest neighbor oxygens, and they will give you a value of 0.217 to 0.315, and you can see you still don't have any of these major elements which will be part of the threefold coordination number. None of them will have. So again, we draw a blank. But now let's go on to this fourfold coordination. Radius ratio 0.225 to 0.414, and the radius of the cation 0.315 to 0.58, and suddenly you start ticking off a few values, few elements. Silicon fits in it. Aluminium fits in it. And phosphorus 0.35 fits in it. So we have silicon, aluminium, and phosphorus. Theoretically, if they're present in a mineral, they should be in a crystal site with fourfold coordination. That means it has 4 nearest neighbor oxygens. So silicon, aluminium, and phosphorus will fit that slot well. But the other elements, they would clearly be incompatible in such a site. Incompatible in such a site. But silicon, aluminium, and phosphorus would fit in well. Let's go over to the next 6-fold coordination. Radius ratio 0.41 to 0.073, and you have radius of the cation 0.58 to 1.024, and now you have a whole range of elements that are competing in this site. Let us look. Titanium, iron, manganese, magnesium, calcium, and the else. Titanium, iron, manganese, magnesium, calcium. These fit into fourfold coordination, sixfold coordination. That means there are 6 nearest neighbor coordinating oxygen atoms around it. So now we have eliminated these elements, yes, and also calcium, and I have forgotten to tell you, here you can have a little bit of sodium, 0.97 angstroms. So you're left with now a few elements, not many more left. Potassium, 1.33 angstroms. So there you go. Potassium could be a candidate for 8-fold coordination or higher coordination. So that means to say that if you have a mineral and if you have any of these elements, they are not going to go anywhere in the minerals, but they are going to sit at particular sites with particular coordination number or nearest neighbor oxygen surrounding it. This is very, very crucial to understand this. That not all elements will be there in all sites. There is specific elements which are compatible at those sites, and then the rest of the elements are incompatible in this site. There is a little problem here. This element, aluminium, Al3+, is 0.51. It's not, you can see here, it should be, ideally, it should be tetrahedral site, but it is also very close to a 6-fold coordination. So aluminium can occur both ways. Similarly, calcium and sodium, here you see calcium and sodium, 0.99, 0.97, it's touch and go. If it has a little bit less value, it will go into 8-fold and other coordinations. Now, remember, all these values, you can ask me why we have this range. It is because as we did in a square or as we did it in a cube, we took a highly idealized structure. But if you happen to give a little torque to those structures, that means this is not a perfect cube or not a perfect square, you could still have some tolerance for that structure, so the major things can be accommodated. So there is a variation in the accommodation space can be created, and then many of the values that we have taken here are very idealized values, but these values are also a little bit flexible. So what happens, these values that I am given are good as a guide, but they are not absolute. You will not find, say for example, in a mineral called quartzite, silicon does not occur as a 4-fold system, but in a 6-fold system. It doesn't. So there can be distortions in the arrangements. These perfect numbers that you have, they are not as unique as I have shown them. There is a tolerance, and so the geometry that you generate with them, they have also certain tolerances. But overall, this would be a good way to start our knowledge start our discussions. This is very important, you please remember. Also, I have derived the radius ratio for a square, perfect square and a perfect cube. These are easy. But you have to know how to derive RC by RA value, for example, for 6-fold coordination, for 12-fold coordination. How do you calculate RC by RA value? And this I will not say, you have to read it up yourself. Having said this, we will now move on to the silicon oxygen. Remember, silicon oxygen are the two dominant elements, that make up of the crust and the mantle. So we will talk a little bit about them. Now, essentially, this is a 4-fold coordination. So, the silicon-oxygen geometry is not like 4-fold coordination. That means 4 nearest neighbor oxygens. But in silicon-oxygen, they are not arranged in a plane. In fact, they are arranged in a tetrahedron. So, for example, silicon-oxygen tetrahedra looks like this, where these are the oxygen atoms, and right at the center you have a silicon. Now these are oxygens. 2 minus, 2 minus, 2 minus, and this one also 2 minus. So you can see for the oxygen, one, you have the silicon-oxygen bond, and the other bond is free. Similarly, you have 4 negative charges on SiO4 tetrahedra. SiO4 tetrahedra, you have 4 negative charges which have to be balanced to make it electrically neutral. Now, what will be the length of silicon-oxygen bonding? So, if you take a simple ionic bonding, then you can see oxygen is 1.40 and silicon is 0.42. So, if just smugly attached, then it should be silicon-oxygen bonding should be 1.40 plus 0.42 angstroms, and that should be 1.82 angstroms. But if we do this, then we are saying that it is ionically bonded. Have you understood? They are just touching each other. There is no covalency involved in this. But we know from our electronegativity angle that it is only 40% ionic and 60% covalent. So if this we do, then the silicon-oxygen actual bond length is 1.62 angstroms. The actual experimental bond length of silicon-oxygen in a SiO4 tetrahedra is 1.62 angstroms, not 1.82 angstroms, because there is only 40% of ionic bonding. So obviously there is an overlap of the outer electron clouds. So both share each other, like you know of the covalent bonds. There is another point to it. The silicon-oxygen tetrahedra, it is its coordination number. We know of 2, 3, 4, 6, 8, 12. The coordination number of an SiO4 tetrahedra is 4.3. It is not 4. It is 4.3. Is the coordination number of the SiO4 tetrahedra. So essentially what I am trying to say is that SiO4 tetrahedra is not a very regular tetrahedra. There is distortion in the tetrahedra. Have you understood? There is a distortion in the tetrahedra. And if you look at this tetrahedra, if you look at the base of the tetrahedra, there are 3 oxygen bonds, free bonds on one plane. Whereas on the top there is only 1 unpaired electrons. So if you try to attach 2 SiO4 tetra base on, there is strong amount of repulsion. But the repulsion, the amount of repulsion, if you are joining the vertices of the tetrahedron, is much, much less. Have you understood? So, here at the vertex, the repulsion is much less, and if you are looking at the base, the repulsion is much more. So, there is an amount of polarity in SiO4 bonding. Now, I want you to find out Rc by Ra of a tetrahedra. I want you to do this yourself. That means, I am repeating slowly so that you understand. I want you to find out the Rc by Ra of a regular tetrahedron. Not the distorted tetrahedron, regular tetrahedron, where 4 oxygen atoms are arranged in the form of a tetrahedra. So if you have seen table tennis balls, So you place 3 table tennis balls in the form of an equilateral triangle and put a table tennis ball on the gap. So you will have a small gap inside the 4 table tennis balls. I want you to find out the RC by RA of the value. I will not tell you how to find out, but I will give you the value as 0.225. That value you should get. You can look up wherever you want, but you should try to derive the RC by RA of a regular tetrahedron, which is 0.225. Also, there is this angle, or called OSIO bond angle. What is the O's oxygen, silicon, oxygen bond angle between this? These are very, very important characters of a silicated mineral. Now, let's go over to something else. Just before we go into the details of structure, I would like to say, for example, if I take a mineral Mg2SiO4, you know this very well, it's phosphorite. And then if you have Fe2SiO4, this is pyrite. So the mineral essentially is Mg, Fe whole twice SiO4. That's all. Of course, there can be manganese here also. Now there is an interesting thing. Silicon occurs in 4-fold structures, 4-fold sites. So these are, silicon is on a tetrahedral coordination. So silicon is surrounded by 4 oxygen atoms in a unit cell. But magnesium and iron, they occur in a 6-fold structure from my earlier table. So in this mineral, magnesium and iron occurs in octahedral coordination, whereas silicon occurs in a 4-fold coordination, tetrahedral coordination. Similarly, now there is a problem here, as you can see quickly, because we will come to this later in great detail. You see, in this structure, magnesium and iron are both participants. In this structure. So, the important point is, how will a mineral accommodate iron and magnesium in its crystal structure? What should be the control of it? We will study this based on pyroxene, in possibly the 3rd lecture. But the important point is, magnesium and iron, remember, 0.74 was the ionic radius of iron, and 0.66 is the ionic radius of magnesium. Magnesium is smaller than iron. But if we take an olivine and analyze it, you will find them that they are both in this crystal structure, octahedral crystal structure. And there are 2 octahedral sites and 1 tetrahedral site. Now if you do this, size-wise, there is no charge difference. Between magnesium is 2 plus, iron is 2 plus, there is no charge difference. So all the difference that will be controlled by is the size difference. Size matters. Size difference. Now then the question comes, the first question that should come to your mind. We have 2 octahedral structures. 2 octahedral sites. The first question that you should ask yourself, are the 2 octahedral sites energetically same, or are they size-wise same? For example, say I do this, magnesium iron, octahedral M1, magnesium iron, octahedral M2, silicon 4-fold O4. How is this different? Now you see what I've done. There are two octahedral sides. I have now split it into two sides. One is M1, both are octahedral coordination. That means both sides are surrounded by nearest neighbor 6 oxygen atoms. But I have separated them out. And the question now remains, if both the sides have the same shape and size, do they have it? If they have it, then logically, magnesium should prefer the smaller side because it has a smaller ionic range. Iron, on the other hand, it should try to accommodate itself more in the larger side, M2. Is it that then M1 and M2 have the same specification, size specifications, or they are different? If they are different, then magnesium by iron ratio in the M1 side and magnesium by iron ratio in the N2 side will be different. Clearly will be different. Because both have different shapes. But if they have the same shape, then of course you would expect them to have the same ratio. It's just like a 6 feet old person would prefer to get in through a door which fits his height. But if you have a 6 feet person, a 2 feet person, he can slide into a smaller door. So it's like that. If the two sides are different, then magnesium iron will be partitioned differently. Have you understood? But we will go to it when we are talking of pyroxides. What I am trying to tell you at the moment is, when you take a mineral, say for example, let's take this mineral, K, Mg, Fe, 3, Al, Si, 3, O10, OH4+. This is the formula of a biotite. If you take the iron end member, it would be anite. If you take the magnesium end member, it would be phlogopite. But you have 4-fold coordination, you have 6-fold coordination, and here you have 10 to 12-fold coordination. You have different specific sites in the crystal structure. Have you understood it? Now, before we go into pyroxenes, I want to clarify a few things before going. 4-fold coordination is an important coordination to understand things. 4-fold coordination. 4 oxygen atoms or 4 nearest neighbor atoms. You can arrange it as I had drawn before in terms of a square, and then Rc by Ra of that was 0.414. But I could have also arranged these oxygen atoms in the form of a tetrahedron. Have you understood? And then the Rc by Ra value would be 0.225. Now see here. I have shown you before that the accommodation of a cation within oxygens or anions is controlled by the number of coordinating anions. But here, the number of coordinating anions is the same. What is different is the packing. Here, in this, you have 3 small balls and a ball on it. So it's like a tetrahedron, and here you have 4 balls on a table, placed on table, 4 planes. Difference between this and this is in the packing, not on the number of nearest neighbors. Both are 4. So, but you can see RC by RA value are dramatically. So the important point is that not only the nearest neighbor anions are important, even the packing of those anions, of the same number of anions, would also change the RC by RA value, or the accommodation of a particular element in a crystal structure. So both the number and the type of packing determines which element will go where in a crystal structure. Now, I will not have much time to go into the thermodynamics of it, but I will introduce you to a very interesting fact. The thermodynamics we will do in the next lecture. Let me draw a diagram. Now, I must confess I'm not good at drawing images. So please excuse me, but if you look up at the internet for orthopyroxene crystal structure, there are magnificent images, will tell you the same thing. But you can just look it up yourself. I'm not good at all this. Yeah? So, this is the structure of an orthorhombic pyroxene. This is how an orthopyroxene crystal looks, where A is towards U, it's an orthorhombic system, B is to the right positive end, and C is the vertical end, where you have 2 sets of cleavage. So bar 110 and 110, which intersect at 90 degrees. So if you look down the tunnel, this is the crystal structure that you will find. What is that? As you know, in the orthopyroxene, where you have, single chains and double chain silicates. I'm not going into that. You're supposed to know it. So these are silicon SiO4 tetrahedra coming in pairs. SiO4 tetrahedra coming in pairs. In between all of those, there are silicon atoms. In each of this there are silicon atoms, and these are the apices are all oxygen atoms. You can have a look at the internet, and there are wonderful images, skeleton images, that gives you a very good idea. Now here, there are two types of circles given here. This one is called the M1 site, and this one is called the M2 site. In this, you have to find it out. These M means metals. These metal ions are surrounded by each of them are surrounded by 6 nearest neighbor oxygen atoms. Some are called. So where you have the opposite apices, there you have the M1 site. These are all octahedral sites. Both of them are octahedral sites. They occur between the apices of the opposing tetrahedrons. And these ones are between the bases of the tetrahedra. Remember, these bases have larger number of oxygen atoms, so they are repulsive in nature. There is more space, and oxygen atoms occur between the bases of the opposing tetrahedra. And M1 occurs at the apices of the orthoperoxide tetrahedra. And this is the structure that follows. Have you understood? So this is the orthoperoxide structure. You're looking through C, and this is B, and this is A, and this is A. This is how the structure is. So essentially, C is looking down this channel, out of which the adjacent tetrahedra are pointing the reverse way. If the larger octahedra occurs at the basis of the opposing tetrahedra, whereas the smaller M1 ions occur at the apices of the opposing tetrahedra. This is the geometry of orthoperoxide. Now, having done this, let me tell you a little bit about the formula for orthoperoxide. Now comes to us. You know the formula as Mg2Si2O6. The formulas are Fe2Si2O6. So now we have a situation where we have So this is how the formula looks like. You have magnesium ion in the M1 side, which is smaller, as you can see from the smaller side, and M2, which is larger. It also contains magnesium and iron. Silicon, there is 2 tetrahedral sites. There are occupancies, but for the moment we ignore that aspect for the moment now. Have you understood? So this is the overall site of the orthoperoxide crystal structure. Now let me give you a little bit more insight into this M1 and M2 structures, which have different sizes. We know magnesium and iron have different sizes. 0.64 for magnesium, 0.66 for magnesium, 0.74 for iron. And similarly, M1 and M2 site, M1 site is smaller, M2 site is larger. Now, these are deeper insights into the M1 and M2 structure. Now, metal oxygen, the metal is here, surrounded by 6 oxygen atoms. You can see here, surrounded by 6 oxygen atoms. The metal oxygen distances, there will be 6 such distances. Metal oxygen 6 distances. They vary between 2.74 angstroms to 2.17 angstroms. With a mean value, metal oxygen value of 2.10 angstroms. But the M2 site, again you have a metal surrounded by 6 oxygen atoms, but the metal oxygen distance varies between 2.04 to 2.62 angstroms. Have you understood? 2.0 to 2.62 angstroms. And the average value is 2.23 angstroms. So you can see, if this is the octahedron, that means, you remember, very simple photograph of octahedron is this. So these are the octahedrons. So the metal oxygen distance from this 4 and the 1 and the 1 below, it's 2.10 and 2.23 average. That means the M2 site is larger compared to the M1 site. And the orientation of the axis of these two, they are not, it's in the orthorhombic system, so it should be parallel 90 degree. It is not, A, B and C all at 90 degrees, but it's not 90 degree, it's rotated off 90 degree. So the metal MO octahedron is rotated 7.3 degrees from the 90 degree deviation. The M2 is shifted by a thrice the amount to 22 degree from 90 degrees. Now, in the next lecture, we will talk a little more about, and wonderfully about, thermodynamics, what controls. So magnesium and iron, magnesium 0.66, iron 0.74 angstrom, they have a charge difference. They want to go into 2 houses which have different sizes. How are the things going to pan out in the end? This we will talk in the next class. Thank you. Yes.